Let's do something interesting today. What you observed now was a pendulum with two different masses, but they completed a to and fro oscillation in the same time.
That feels kind of counterintuitive, right? I mean, you would expect that if the pendulum is heavier, that it should oscillate faster, but the mass of the system doesn't seem to affect it. Let's find out why on today's episode. Hi, I'm Nikhilesh.
And I'm Kushal.
We're the two Grok scientists.
Actually, if you think about it, the acceleration due to gravity is independent of the mass of the object. Therefore, it makes sense that the time period doesn't change with mass.
Hey Kushal, what happens if we change the length of the string?
Okay, the length of the string seemed to have affected the time period. The shorter one seemed to have oscillated faster. It looks like a lot of different parameters affect the system, and mass clearly wasn't one of them. I'm sure the acceleration due to gravity has an effect because that is what is causing the bob to move in the first place.
So you can see that there are quite a few parameters that affect the system dynamics. So if a physical system has many parameters, then it becomes quite confusing to keep track of which parameter affects the system dynamics. And that's where a tool like dimensional analysis becomes useful.
Consider the different parameters that could possibly affect the time period of a pendulum. First, there is obviously the time period which we want to measure. Then we have the mass, length of the string, and acceleration due to gravity. We assume that the velocity at the start is 0 and the angle which we drop it from is very small so that the behavior is linear. All these parameters that we have shown you have physical dimensions.
For non-dimensional analysis, as the name suggests, every physical system can be broken down into parameters that do not have dimensions. For the pendulum system, since we want to understand what the time period of the system is, let us see in what way we can non-dimensionalize time. A little bit of manipulation, which comes from experience, gives the following formula.
You see that the expression from non-dimensional analysis matches the exact formula of a simple pendulum multiplied by a constant. So suppose you did the same experiment on the moon, where the gravity is 1/6 of that on Earth, you can then play with the length of the string to ensure that the time period doesn't change without even knowing the exact formula. That is the power of dimension analysis. It's pretty amazing that just by physical intuition we're able to characterize the system based on its non-dimensional parameters.
If you think about it, we define dimensions like mass, length, or time for our reference, but physics itself is independent of dimensions.
Wow. Okay, now we can characterize the system based on its non-dimensional parameters. But where else is it used?
Dimensional analysis, or scaling as it is sometimes referred to, is extremely important in fluid mechanics. Have you ever wondered how aeroplanes are tested before flying them? The answer, as you probably already know, is wind tunnels. Even the Wright brothers use wind tunnels to test their planes. But you can't fit an Airbus A380 in any wind tunnel in the world. So what do? You just scale it.
The forces that a scaled model experiences cannot be directly compared to the real-life model. So we take out the dimension from this problem by scaling it. The lift on an aeroplane depends on many parameters including size, velocity, viscosity of the fluid, density of the fluid, angle of attack, and so on. If you scale the forces you require, in this case lift, by geometrical parameters of the plane, then the resulting equation can be expressed in terms of non-dimensional parameters which govern the forces on the body at any scale. You see that the resulting equations is much simpler. Non-dimensionalizing this equation reveals one of the most important numbers in fluid mechanics, the Reynolds number. The number contains all the complicated effects of parameters like viscosity, density, and the velocity of the object. By maintaining the same Reynolds number between the scale model and the real flight, we can directly compare the two scaled forces.
The Reynolds number is probably the single most important parameter in fluid mechanics. It characterizes the interplay between the inertial and viscous forces of a flowing fluid. These two forces dictate the behavior of the flow in a particular situation. For example, when viscous forces dominate, the fluid exhibits a laminar and predictable behavior. But as the Reynolds number keeps increasing and the inertial force starts to dominate, the fluid starts becoming turbulent and unpredictable. So, something as simple as the Reynolds number can determine what kind of behavior we can expect from a fluid flow.
Non-dimensional numbers like the Reynolds number have been instrumental in knowledge transfer. Even though it is not possible to replicate experiments in different parts of the world, the use of non-dimensional numbers removes the dependence on dimension, thus enabling us to perform our own experiments which can then be compared with literature. For example, even though the World Cup football was tested in different parts of the world, in different wind tunnels, operating at different conditions, the results could be easily compared by using non-dimensional numbers. Thanks for watching. We hope you enjoyed the video.
And hopefully, now you know that physics is independent of dimensions.
And finally, don't forget to like, share, and subscribe. Bye.